So the last class we proved something like the commutant of Weyl operators or scalars. So today we want to prove something, the irreducibility of the Weyl representation. That is, Weyl operators generates everything in P of X in strong topology. For that we want to prove, so we already seen this von Neumann double commutant theorem for finite dimension. We will prove it for infinite dimension. Okay, that is the aim of, so we will do that and then we will do some unbold operator theory today. So okay. So the first thing is we have defined strong topology. We have defined it using nets or using the convergence. That is equivalent to, we have defined through closed sets. Now we will define through open sets, and then, I mean, because we need it in the proof of double commutant theorem, so we define through open sets. So what is strong topology? So we have a net T lambda containing in B of H. Okay, then we say T lambda converges to T in strong topology if T lambda xi converges to we say T lambda, the net converging to T strongly if T lambda xi converges to T lambda T xi for all xi, point-wise convergence xi. So this is basically the topology generated by these functions f xi, where f xi is a function from B of H to H, where T going to T xi, right? The weakest topology, the minimal topology, which makes all these functions continuous. Okay? This, of course, these functions are continuous. Tn converges to T, then T and xi is point-wise convergence. Uniform convergence, convergence norm will imply point-wise convergence. So here we are only the topology which makes the point-wise convergence continuous. Okay, so this is the topology generated by this. So what is the base for such topology? If you are given a collection of functions, you can take any set and you can take a collection of functions. Any set and you can take a collection of functions. Then you can define the topology to be the minimal topology which makes all those functions continuous. So how will you define the topology? So the function has to be taking value in some topological space. Then only you can do that. Okay. So you take the inverse image of, so we want to make all those functions continuous. So the topology has to be generated by inverse image of open sets. You take the inverse image of open set, take finite intersection, and you arbitrary union, that will give the topology. So you can take the base of the range space, base of the topology of the range space, and take the inverse image, okay, and then take finite intersection, and then union, that will define the topology. Okay, that is clear, no? If you take any set of functions, any collection of functions, then the topology which makes it continuous, the minimal topology, I mean, all these sets has to be there, and the topology, that topology will make it continuous. So it's both the way it's equivalent. That's all right. So I'm saying the topology generated by this function is generated base for this topology. Base, I mean base, what is base means? Base means you take finite intersection in the base, or how do you generate the topology? Base is something, yeah, you have to take finite intersection. No, base is something, when you take arbitrary union, you should get that. Right, okay, yeah. So the base for this topology is I mean, base is something like if you are something is open, usually what is in a topological base, how would you say it's open? Something is open, if you take a point, then you should find what is it, base, something in the base which is contained in there. So you should take finite intersection. Base for the topology is f xi1 inverse of u1 intersection f xi2 inverse of image of u2 intersection f xin inverse of un. So this is a base. This kind of elements or these kind of sets are the base. Okay. Okay. Now this is a base. So we want to talk about neighborhood bases. Okay, neighborhood base. What is a neighborhood? Neighborhood, how is it defined? Usually a neighborhood or a topology is given that's a collection where if you want to say the equivalent, you can define the openness using that equivalent condition. Given a point, you should have a neighborhood around that which is contained in the open set. That is what neighborhood is. Okay. So the neighborhood around a point is, so if we take a T in B of H, okay, then a neighborhood around that T is in, suppose T is, let's assume the T, you should have a neighborhood like this. Okay. F of xi1 inverse u1 up to f of xin inverse un. Okay. R intersection. So this is how, so T is there. So that means you can take a neighborhood to be, you can take all those u1 up to un to be open balls around T of xi, right? And what I'm saying is a neighborhood basis neighborhood around T looks like, I mean, you have arbitrary open sets, but you can take those to be open balls, right? It's enough to take open. Okay. So I'm saying it is a neighbor open set is f xi1 inverse of the open ball around T xi1 some epsilon 1. Okay. Intersection f xin inverse of B of T xin some epsilon n. Now by taking the minimal value, minimal epsilon, I mean, if this is contained in something, it is equivalent to saying you can take epsilon minimum, some other epsilon smaller than this. Okay. So a neighborhood base is given by neighborhood. I will just write the thing. It's clear. I mean, I don't have to write neighborhood basis for the strong topology. Topology is given by, okay, I'm saying f xi inverse I equal to 1 to n, okay, inverse of T xi some single epsilon. I'm just saying there is a single epsilon. You can take the minimum of that epsilon and that will work. It's a finitely limiting, so minimum is greater than 0. So you can take this. So a neighborhood basis which is equal to all those S in B of H such that norm of T xi. So I call this as n epsilon xi1 up to xi. That is how the basis will look. S xi is less than epsilon. Okay. This is how a neighborhood basis for the strong topology looks like. Instead of, I mean, open bar is just given 1 epsilon and a point. Here you have a point, and I mean, the point is not coming from T. I mean, the point is not coming in B of H. The point is actually, I mean, you are taking the inverse image of open ball. So it's a open ball around T xi for each xi. Okay. You take all those S such that it satisfies this. This is a neighborhood basis. If some set is strongly open, if given any T, there is a neighborhood basis around that T, which is completely contained in that. That's what open in strong topology means. That's the definition of openness. That's clear, no? That's clear. Okay. Now we want to use this. So I just want to get it, I mean, write the neighborhood basis clearly. Okay. So this is the neighborhood basis for the strong topology.
Can you repeat what is the neighborhood basis?
Neighborhood basis is a collection of open sets, which when you take finite intersection and other thing, which it's a base for the topology. Okay. Neighborhood is something around a base set around that. That's all. By this, I mean, if some set is open in the strong topology, if given any point in that open, if in that set, there is a set like this around that point, which is completely contained in that. It's like an open ball. So this is not a ordinary metric space. This is not a metric space. So you need an open ball around that. That's all. Okay. Usually, this kind of, see, the open ball is something bounded in a metric space. In this kind of topology, the open balls will be unbounded always. It will not be bounded.
The epsilon should also be.
No, for each epsilon, you have a neighborhood. How do you define open in a metric space? Set is open. If there is a point in that set, there is an open ball. There should exist an epsilon. Okay. For some epsilon, epsilon will vary. For some epsilon, for some xi1 up to xn, you should have a set like this, which is contained in that. If all these things, I am just saying, given a point, there should exist a set like this around that point, which is the neighborhood point. Okay, this is the neighborhood. Okay, so so that it should be completely contained in that. So that's what openness means. Okay, okay. So now we want to use this to prove that. So the double commutant theorem. We have already proved it for finite dimension where there is no topology involved. So if S is contained in B of H and S star equal to S, that is X is in S, implies X star is in S, is self-adjoint set, then the algebra generated by S, okay, is strongly dense in S double commutant. That is, the algebra generated by S closure is equal to S double commutant in the strong topology. If you take the closure, or in other words, this is what is called any algebra which is closed in the strong topology is called von Neumann algebra. Okay, and this says the von Neumann algebra generated by S is S double commutant. And you can see the beauty of this statement. What is the beauty of the statement? That side, algebra generated by S. You forget about that. You take an algebra. You take an algebra. Just you take an algebra. Let A is equal to algebra generated by S, which is just in A. Okay. Then A closure is a topological statement. Is a topological closure. Okay. A closure is a topological closure. In the strong topology. Okay. That is equal to you take the double commutant, which is completely an algebraic operation. You think about that. So that is why this function as whatever operator algebra is an intersection of both analysis and algebra. I mean, you can there will be more algebra, more analysis. It's not clear. Both are combined here. That's a purely topological statement. This is purely an algebraic statement. Okay, these two are same. Okay, so this is the beauty of this theorem.
Sir, last class you also mentioned you can take the closure in weak topology.
Weak topology, which weak topology? There is a weak topology I haven't defined. You can take topology in many things, everything will be same.
You said subspace, not.
No, this is the weak topology we defined in the other class.
Yeah.
That weak topology is what is called given by the dual space. Okay, B of H dual will be very big. Okay, so that is not the weak topology is not the right thing. B of H is other topology. Usually in the operator, there is something called, this is the confusion which is lasting. Nobody is ready to change. I mean, everybody has to agree. There is something called weak topology. T lambda converges to T weakly. Usually by the weak topology in the Banach space weak topology, this means for anything in the dual of B of H, P of T lambda should go to phi of T. But that is not the case. We just say T lambda xi eta goes to T xi eta. This is just a confusion of names, nomenclature. Okay. So this is what is called weak topology, operator weak topology. Okay. So these are two completely different topologies. Strong topology is different from strong topology. There is something called sigma weak topology. That is the weak star topology on B of H. B of H is a Banach space. There is weak topology. I haven't defined weak star topology. Weak star topology is the topology given by the pre-dual, whose dual is this B of H. Okay? That is what weak star topology. See, if you have a Banach space B, then if some x star equal to B, okay, then the weak star, see, if you say phi lambda converges to phi, if and only if phi lambda x converges to phi of x for all x in the pre-dual. Phi acts on that. This is a topology in the dual space. Weak star topology is a topology in the dual space. A Hilbert space is already a dual space. It's a dual of its own. So Hilbert space, weak topology, weak star topology will coincide. Okay. In any reflexive space also it will coincide. The Banach-Alaglu theorem I stated that says that unit ball is weak star compact in the dual. But for a Hilbert space there is no difference, so we use weak topology there. Weak topology itself. So these weak star topology are different. There is a so B of H is a dual space. It's also it's a dual space also. It's a dual of, we define some trace class, no? It's a dual of all trace class operators, which we will prove. Okay.
Sir, but like in the weak star topology, like if a set is bounded in weak star, if and only if it is bounded in the normal topology.
In weak star topology, a set is bounded in weak star topology.
Yeah, if and only if it is bounded in the normal topology on the, like the supreme, that one.
I think so. No, but that's for not for nets.
Dual, so
No, that's for sequence, not for nets, I think.
Oh, okay.
It will not work for net.
So I thought we could do something same for this. So you said the open sets are not usually bounded.
The open sets of weak topology, weak star topology are not bounded.
No, the strong topology.
No, none of this topology open sets are not bounded.
Okay.
But when you, within a bounded set, if you consider, you can take the intersection and define the open sets in that, no? If you have a subset, then you can take the intersection and define open sets, okay? So those open sets, that is different. There it will be not just bounded set, that will be metrizable and it will be a metric space. But in general, weak topology, it's all this topology. I'm saying this is weak star topology. Weak star topology is the pre-dual, topology given by pre-dual. So that is for B of H, the pre-dual is trace class operators, which we will define in the next class there. B of H star equal to B of H. That weak star topology is called a sigma weak topology for some reason. Okay, I'm sorry. It's not my mistake, but my fault. But that is called sigma weak topology. It's supposed to be so-called weak star topology on B of H is called sigma weak topology. So the statement is, if you have an algebra E, star algebra E, then you can take the strong closure, you can take the weak closure, you can take the sigma weak closure, you can take any closure except the norm closure. Okay, everything is same. They are all equal to A double commutant. That is what the theorem is. But I don't want to discuss all the other topology. We will deal only with strong topology. That is enough. Okay? That is norm topology is different. Norm topology is stronger topology. Stronger topology means it will contain more open sets. Okay, so the closure will be, if you take a set, okay, strongly closed set will be already norm closed. So the norm closure will be smaller than that. Okay. So if you take a algebra A, its norm closure is something smaller than the strong closure. Strong closure will be bigger. The norm closed subalgebra, star algebras are called C star algebras. Okay. Strongly closed subalgebras are called Von-Neumann algebras. Okay. And it's also sigma weakly closed in all those things. Those topology, they do not coincide. For algebras, the closures are same. That's all. It's not the topologies are not same. They are different topologies. Convergence may differ. But the closure, when you take for algebras, it's a theorem that algebras, it's all same. Okay. For star algebras, if you take any of these topology except norm topology, it's same. There is something called sigma strong topology, sigma weak topology. So everything will be.
So every C star algebra will always be a one.
Every Von-Neumann algebra will be a C star algebra. Okay? Because C star algebra is norm closed. So it need not be strong closed. Okay? All compact operators which we discussed, that's a C star algebra. It's norm closed. Okay, but it's not if you take finite rank operators, Its norm closure is compact operators. That's what we define. So it's norm closed already, right? So, but if you take the strong closure of all finite rank operators, you get B of H. Okay. That you can prove easily. You take rank 1 projection, you just take the commutant of that. Rank 1 projections. Okay, you take the commutant of that. That will give you B of H. No, that will give you C. Sorry. You double commutant is B of H. So the commutant is C. Okay. Okay. So this is the double commutant theorem we want to prove. So what we want to prove is assume A is an algebra. I mean, assume without loss of generality, assume we want to consider only S is equal to A star algebra. Okay. Then we want to prove that now we know that A is already contained in A double commutant. We know that already. Okay. Because, right? If something A commutant is all those operators commutes with A. Certainly A commutes with A commutant. So A is contained in a double commutant. We only have to prove the other way. What we have to prove is the strong closure of A is A double commutant. That's what we have to prove. So that is given any T in A double commutant, we want something and epsilon greater than 0 and a neighborhood around that. I mean, we given any T and a neighborhood, any neighborhood around that, we have to produce something in A. That's what it means by it's dense, right? Dense means if you take any point in that, okay, and you take in any neighborhood or any open set will contain a neighborhood. Okay, any neighborhood that should contain a point from that, whatever you are claiming to be dense. Right? That is what dense is. Okay, so we need to prove. Given T and given a neighborhood, is given by xi1 up to xn and epsilon greater than 0. Okay, there exists a S in A such that S is in such that T is in that or S is in that, whatever mean. Such that I mean, S is, it doesn't matter. S is in that neighborhood, whatever. That neighborhood means there exists a S such that norm of T xi I minus S xi I is less than epsilon for all I. Okay. Given xi1 up to xn, that's what it is in that neighborhood, right? That neighborhood is given by this. That neighborhood is there. Given any T, you should find a S and a neighborhood around T, you should find something in the dense set, something in the set which you are claiming to be dense. To prove dense, that's what you have to do. So that's what I am claiming. So given any epsilon and xi1 up to xn, we want to prove there exists a S in A such that this happens. Okay. So we will do the same thing. We will consider for one xi, prove this, and then take the tensor product. Similar, if you remember the proof for a finite dimension, that's what we did. We did for one xi, then there it is finite dimension. So we took a linearly independent one and proved it. Here, instead of that, we have finitely. Here also the same proof. It's exactly same proof. I can actually leave it as an exercise. But anyway, so the claim is it works for one xi and epsilon. That's what we want to prove first. Then for n xi, it's the same thing. The same way we did for finite dimension. Okay. So claim it works for n equal to 1. Okay, n equal to 1. So this is I up to I equal to 1 to n. Okay, so works for n equal to 1. So what do we do is we have a Hilbert space H. Let K equal to, you take the algebra A. Okay, and it works for n equal to 1 and a vector xi. Okay, one single vector xi. I mean, it's not xi1 up to xn. There is only one vector, it works. So I'll take K equal to A xi. You take the algebra, you add the algebra on this one single vector. Okay. I mean, you take, this is just T xi where T coming from, that will be a vector space. Then you take the closure inside H. Okay. This is your K.
Closure is strong to
H. This is just H. There is no strong. This is happening inside H. Okay. This is a subspace. Okay. And P is the projection from H to K. The projection, orthogonal projection. Okay. Then what happens? P, see, this H looks like this, right? Then K is invariant under P. That is, if you have any P of any ASI for A in A. Okay. How did you prove last time? P of ASI is no. Then K is invariant under A. I'm sorry. Yeah, K is invariant under A. I'm sorry. Not P. K is invariant. That is stupid statement because that is the projection. No? So K is invariant under A for all operators in A. That is AK is contained in K and AK per is contained in, I mean, first statement is what called reducing. This is what invariance means. It will look like a direction. See, if you have any H looks like K direction, K per. Okay. So any operator can be written as some T1, T2, T3, T4. The T1 is an operator from K to K. T2 is an operator from K to K per. T3 is an operator from K per to K. T4 is an operator from K per to K per. So that is how it will look like. It will act as a matrix, xi1, xi2, right? It's a direction. So it will look like that. Okay. So I am just saying that this A, all these operators in A, this algebra takes K into K per to K per. Okay, that's what I want to say. So it is clearly A acting on any ASI is again, I mean, it's clearly A takes K into K. That is clear because K is defined to be ASI. Okay. If you apply A, it's going to be again inside. So clearly, AK is contained in K, of course. Because if you take K is like any, I mean, for ASIs are dense set. So it takes the dense set inside the dense set, it will take the closure also inside that. Okay. That is because as I mean, A is all bounded operators. So if it takes all the dense, K is the closure of ASI. So K, all operators in A takes ASI into the dense subspace into K itself. It will take K into K. The closure also it will be, since K is closed. Okay. K is closed and by definition. Okay. And by definition. Okay. Now we want to consider the orthogonal complement. Okay. So let eta be orthogonal to K. Okay. Then A eta. Okay. A eta acting on some Bzi. Okay. That is equal to eta acting on A star Bzi. Right. Which is equal to 0 because this is in again K. Bzi is in K. A star B is in A. Okay. It's in the algebra. So this is in K. This is in ASI. ASI, which is contained in K. But eta is in K perp, so it is 0. Okay. So this implies A of K perp is contained in K perp. Okay. So this implies P is in A commutant. I mean, this is all operators in the script A, the algebra A, takes K into K, K perp into K perp. There is no off diagonal elements. Okay. It will look like this. A looks like some A1, A2, 0, 0. That means it commutes with P. P is just this. Okay. It will commute with this. P is just this with respect to that. 1 is the corresponding one on that. So it will look like that. So P is in A commutant. Okay. Now, so M is in A double commutant. Then, of course, MP equal to PM. Okay. This implies M of K is contained in K, right? M is in double commutant. M of K is contained in K, which is equal to A xi closure. That is given epsilon greater than 0, there exists a xi such that m xi minus a xi is less than epsilon. Okay. So this is works for one single xi. Now we want to prove it for xi1 up to xi1. So now let xi1 up to xin is in H and epsilon be greater than 0. Now we want to produce the same thing. Given a m in double commutant, we want to produce something in A, script A, such that that inequality is satisfied. M xi1 minus A xi1, M xi A minus A xi A is less than epsilon. So for that, what we do is the following. Let Hn, Hn, okay, Hn equal to direct sum of H. You take the H direct sum n times, okay? Sorry, n equal to I equal to 1 to n. Okay, you take the direct sum of H n times. Okay, that is Hn. Okay, then you define pi from B of H to B of Hn by T going to T, 0 everywhere. The diagonal T. Okay, this is pi of T. Then this we have already done. Should I do it? Pi of A commutant equal to Mn of A commutant. Okay. What's the problem? Did I write something wrong? What?
Nothing. I was just saying the equation is given with H subscript n is everything. Subscript 5.
Okay, correct. So I put it. That's right. So what shall I write? Yeah, it is weird. Put it on the top. Okay, let us just have it as this. H tilde. H tilde. H tilde. Okay. Yeah, yeah. Nth one is that H tilde. Okay. This is okay. This is 0 anyway. Okay. Big 0. 0, 0, 0, everywhere 0. So the commutant of pi of A is just diagonal elements A. You just compute the commutant. You take some T1, T2, T1, Tij. You take an operator Tij. It commutes with T like this. Write the conditions. You will get that all those Tij should come from A commutant. That's what the condition. That's all. Okay. Any such thing will commute, and you can directly write it down. Okay. Okay. And Mn A double commutant, which is equal to pi of A double commutant, will be equal to pi of A double commutant. So if you now you have a matrix full of elements coming from A commutant. Okay. This Mn of A commutant is matrix. I mean, it's a matrix element with entries coming from A commutant. If you take the commutant of that in B of Hn, I mean in B of H tilde, okay, that will be a diagonal element, but the diagonal elements, I mean, if the same element, not just diagonal element, it's like a scalar element, okay, which is and that element should come from A double commutant, pi of A double commutant. Okay. Pi of A double commutant. So now, given M in A double commutant, okay, pi of M is in pi of A double commutant. Okay. So there exists, and so given by the earlier proposition, which we have used for n equal to 1. Now you take the Hilbert space, I mean, replace the algebra A by pi of A, and you get the given xi1 up to given xi1 up to xn, which is in that H tilde now. Okay, which is in the direction H tilde. Okay, and epsilon greater than 0. Okay. I mean, there exists a pi of A in A, pi of A. A in A. Well, it will, if you have an epsilon, the total thing is bounded by epsilon, but it's clear, you adjust it and such that pi of A minus pi of M acting on that xi1 up to xm is less than epsilon. Of course, I mean, this is for how do you define the direct sum of this? That will be sum of those things, right? I mean, it will be norm square. Sorry, it's a square of the norm sum. Direct sum is defined as first entries. I mean, it's the square of the entries, right? But then you choose the epsilon wisely, and then I mean, it's okay. So if you want, you put it epsilon prime or something. This is true for any epsilon prime. So given epsilon, given any other epsilon, given eta may be greater than 0, there exists xi1 up to xn such that pi of A is just, I mean, the pi of A minus pi of M acting on xi is just, which is just the pi of, which is just A minus M xi1, A minus M xi2 up to A minus M xn, right? It is norm. Okay. This is less than epsilon. You can choose eta such that, I mean, it's clear. And for E, this works for every epsilon. So given any epsilon, so this, that need not write, you fill it up. Okay. No, given epsilon greater than 0 and I'm sorry, it's not given and xn given. We will get the A1. So this implies the proof. Okay. Proof follows from this. Okay, it's done. So to take the strong closure, you have to take the double commutant. Okay, now what we have.
What are you written in the last one? Like there exists A in A such that.
I just applied the thing. Pi of A minus pi of M acting on xi1 up to xm. Pi of A minus M, xi1, A minus M, xi2. That's what it is now.
No, like what is the first?
Given epsilon greater than 0, xi1 up to xn in H, there exists A in A such that A minus M xi1 up to. This is just the norm of the direct sum. Right?
Like what is there after the norm sign? There is something I don't know.
After the norm sign, there is nothing. After the norm sign, less than epsilon. This is the norm. This is the norm. Yeah, that's a bracket. I have just evaluated that, nothing else. I have removed the pi, that's all, okay? The pi is that representation, I just removed it. Okay. So we have proved for a hill, I mean, H is any Hilbert space, H is any Hilbert space. Yes. Gamma H is the Fock space, symmetric Fock space. Okay. Then W of X, X coming from H, the commutant is equal to C. So this implies the von Neumann algebra generated by W of X, X in H, is equal to B of the Fock space. Okay. It generates all operators. And the nice thing is that means the algebra generated by the Weyl operators are strongly dense in B of gamma of H. Okay. That is operators like the summation lambda I W of Xi, I equal to 1 to n. These kind of elements. Okay. Xi is in H and lambda I in C. See, the nice thing about the Weyl operators are they don't commute. W of X1 and W of X2 don't commute. But you can compose them to get W of X1 plus 2 up to a scalar. They commute up to a scalar. So the algebra generated by that will be just linear combination of that. See, to get an algebra generated by some elements, you have to take all sorts of products and all sorts of sum to get the algebra. Okay, arbitrary product, arbitrary sum, you have to take finite sum, finite linear combination. But you don't have to take finite, any product will again look like W of that. Product of W's will look like scalar times W's. Okay. So it will look like this. So these kind of vectors are dense, are strongly dense. Dense in B of gamma SH. So that's all. So this is what we want to prove. This means W of X does not have any invariant subspace. If it has an invariant subspace, B of that subspace only it will generate. I don't want to go through it. It will all be clear if you do some operator theory later or something. Okay. I mean, there is no reducing subspace for all the Weyl operators. So it's Weyl, this is Weyl representation is irreducible. Okay. There is no invariant subspace for the Weyl representation. That's what this is. Okay. So we have taken 45 minutes for this. Okay. Maybe another 45 minutes to prove one theorem in unbounded operator. So I will start some unbounded operator theory. To look at this, I will